All right, this is exam 3 for Physics 102, Spring 23. This is the latter half of Chapter 4 and all of Chapter 5. First, I have the multi-loop circuit. I want to know the three currents, I1, I2, and I3. First, I'm going to choose the directions of the currents. No particular reason for choosing them, just because. And now I'm going to do the loops. I'm going to choose my loops wisely. First, I'm going to take the right loop. Notice that this part of the circuit, that branch of the circuit, doesn't have a resistor in it, so that's why I choose that right loop, and also I'll choose the big loop as well. Let's start right here, and I'll go in this direction. So I have minus 2I2, minus 2 is equal to 0, and I can solve this for I2 is equal to 2 divided by negative 2, which is negative 1 amp. I'm going to do the big loop now. I'll start in the same spot and go in that direction. That's plus 6 plus 2I1 minus 2 is equal to 0. That's 2I1 is equal to negative 4, negative 2 amps. Now I'm going to use the junction rule. Figure out I3. I'll choose this junction. I have I3 coming in and I1 coming in. So I have I3 plus I1 is equal to I2. Looks like I need I3. That's equal to I2 minus I1. That's negative 1 minus negative 2. Notice how I kept the negative signs on both I1 and I2. That's 2 minus 1, that's 1 amp. So I3 is 1 amp. So I have I1 is 2 amps. It's like I chose the direction incorrectly, so while I'd chosen it up, the direction is actually down. I2 is 1 amp. While I'd chosen it down, it should be up. And I3 is 1 amp. I'd chosen it up, and it is up because this current is positive. All right, I'll be looking for both the magnitude of the current and the direction. All right, here I have a charging capacitor, and I want to know when the voltage is 12 volts. Let's look at our equation sheet. The voltage for a charging capacitor is given by this, V naught 1 minus e to the minus t over RC. So I'm going to have V equals V naught times 1 minus e to the minus t over RC. And I need to solve that for t. So this is part A, where I solve this for t. Um, so I have 12 is equal to the maximum voltage, that's 24, minus, I'm going to go ahead and distribute that 24 times e to the minus t, and then RC is 3 times 4, that's 12 seconds. So this is my equation, so I have, take my 24 over, so I get negative 12 divided by negative 24 is equal to e to the minus t over 12. So that's 1/2 equals e to the minus t over 12. I take the natural log of both sides. That natural log gets rid of uh, that that e. So if I take the natural log of 1/2, I get negative 0.69. That negative goes away. I multiply that times 12 to get t. I get 8.3 seconds. Actually, it should be 8.32 seconds. All right, at t equal 12 seconds, what is the percentage of the maximum charge on the capacitor? So again, let's look at our equation sheet. So for a charging capacitor, our charge looks like this, Q times 1 minus e to, so I know for part B that Q is equal to Q times 1 minus e to the minus t over RC. That's for a charging capacitor. Q is equal to CV. I'm going to do that right up here. Equals to CV, which is equal to, actually, no, I don't even write. Yeah, Q is equal to CV Actually, no, I don't need to do that because I just want to know what is the percentage of the maximum. So I'm just looking for what is Q divided by Q, which is going to be 1 minus e to the minus t over RC. And then that'll give me the percentage of what percentage of the total charge is on the capacitor. So that's going to be 1 minus e to the minus 12 over 12. So I'm at one time constant. Um, and 63%, or 0.63, or I would take 63%. Either one of those I would take as an answer. All right, and then finally sketch a graph of current versus time. So the current versus time is given by I naught e to the minus t over RC. Let's look back at our equation sheet actually. So here, current, this is for charging or discharging, and it says V over R, but that's our initial current. So it's going to start out big and then go small. So the current is going to look like an exponential function, roughly sketched out, look like that. All right. Proton approaches a wire of 4 amps as shown in this figure. There's its velocity and the distance. I want to know the direction and magnitude of the magnetic field. So at this point, there is a magnetic field. I imagine my thumb going in the direction of the direction of the current, and then my fingers wrap around to give me the magnetic field here, which is out of the page. On this side, by the way, it's going to be into the page. So for part A, it's going to be out of page. That's part of your answer. The other part of your answer is I want you to calculate that magnetic field. Look back at our equation sheet. We have two equations that are really similar. We have this one and this one. Now remember this one because it has the N that it's referring to the loops of wires. So I know that I have this mu naught I over 2 pi r. So B is equal to mu naught I over 2 pi r. Mu naught is 4 pi times 10 to the minus 7. That's my pi right there. 4 pi times 10 to the minus 7. That's on your equation sheet. If you look back over here, it is right here. Um, and then I gave you in the problem is 4 amps divided by 2 pi times R, which is 0.2. Meters cancels there. 2 times zero point 0.2 is 0.4. So that cancels with this and leaves a 10. So it looks like I have 40 times 10 to the minus 7 Tesla. Or what's that? Yeah, 4 microtesla. We'll just give it to that. 40 times 10 to the minus 7 Tesla. And now it's out of the page. So that's part of the answer, and this is the other part of the answer. Now, next part is I want to know what is the direction magnitude of the magnetic force on the proton, because I have this proton going with the velocity in this direction, a magnetic field in this direction. So what is the direction of the force that it feels? Well, the velocity is down, the magnetic field is out of the page, and so that force is going to be in that direction, so it's to the left. That's part of the answer. And then I can calculate that force, QVB, sine of theta. Theta here is 90 degrees, so it's just QVB. Q is 1.6 times 10 to the minus 19 coulombs times V, which was given 3 times 10 to the fifth meters per second. And then B is 40 times 10 to the minus 7 Tesla. All right, so I can do that. I get 1.9 times 10 to the minus 19 newtons. All right, so that's the force that it feels to the left. And that's it for the free response. So um, let's look at multiple choice. Which of these is a correct statement of Kirchhoff's rules? Remember, that was either the loop rule or the junction rule. The sum of the currents around the loop must equal 0. Not true. It's the sum of the voltages The voltage on a resistor is inversely proportional to the current. Let's see, I know that the voltage is equal to I times R. That means it's not inversely, it's directly proportional. The voltages entering a junction will equal the voltages out of the junction. So it's the currents that will equal the currents out. That's the junction rule. Um, the currents in a circuit will all be the same. No, no, probably not. Most of the time, not for a multi-loop circuit, especially. So E is the right answer. All right, what is the current in this circuit? Okay, so I want to know what I is. Well, I know that I have 12 amps coming in here, so that means I have 4 amps going right there. That means that in this little section I have 8 amps, but then 3 amps splits off, so I must have 5 amps here. So that must be the answer. Yeah, so C. But notice I can go from it this other way too. That if I have uh, 3 and 4 amps, then I must have 7 amps there. And if I have 12 amps coming out of here, then 7 plus 5 equals 12. So everything is just right, actually. Uh, which of these equations are correct? Let's start with the first one. I have I1 and I3 coming in and I2 going out, so it should be 3 and 2, so that's not right. Here I have minus 2I1. I'm starting right here and going in this direction. Minus 2I1 minus 6, so far so good, minus 9I2, that's right, and that's right, so this one's right. 3 minus 2I1, 3 minus 2I1 plus 4I3. Okay, I should need to lose this I3 and that becomes a negative, so that one's not right. And then I have minus 6 minus 9I2 plus 3 minus 2I1. Yeah, that looks right, so B is the right answer. What is the current through the 2 ohm resistor? Okay, so the best way to do this is to look at the big loop. I'm going to start here and write the equation. 3 minus 2I1 minus 4 is equal to 0. That's negative 1 minus 2I1 equals 0. So I1 is equal to negative 1/2. Although I wasn't really asking for the direction, I just want to know the magnitude. So 4 is D. Which of these statements about a household circuit is true? Grounding electrical devices protects the user from faulty devices. Yes. The GFCI protects the user from unsafe or wet conditions. Yes, that is correct. The circuit breaker turns off if the incoming current exceeds the outgoing current. No, that's the GFCI. All devices operate at the same voltage. Yes, so 1, 2, and 4. What does this device do? Well, this is a circuit breaker, and it does that. None of these others. This is the grounding, although your circuit breaker box is grounded. This is GFI. But you can have circuits in your circuit breaker box that are enabled with a GFI so that every outlet and every device on that circuit is ground fault interrupt circuit. It has this GFCI protection. Stable source of voltage, no, though we do have devices that do provide a stable source of voltage. That's called an uninterruptible power supply. We have them on a number of our instruments in the chemistry department. It's just to provide, protect you from spikes in the power. Or turns off if IN, no, that would be a GFI. All right. Circuit breaker, you have these devices, and then I add a blender, and it turns off. All right, so the 1200 watt, that's this power, so the current that it pulls is equal to P over V, 1200 over 120, because everything operates at 120 volts, so that's 10 amps. In a similar way, the 720 watt fan is 720 over 120, that's 6 amps. So I have 16 amps, and it's chugging along just fine. And then I add another 2 amps, that's a 240 watt blender, so then I now have 18 amps. So somewhere between 16 and 18 is where the circuit breaker turns off, and that's going to be the answer is A. Capacitor discharges over 10 time constants, means it's fully discharged. Which of these represents the voltage versus time? Okay, so the voltage will start out Discharging. Yeah, we'll start out big and decrease with time. So um, the answer is going to be D. If you're not sure about that, go to the equation sheet. I'm looking for voltage for a discharging capacitor. Voltage for discharging looks like that, e to the minus t over RC. You need to remember that e to the minus t over RC, that decay function always looks like this. While 1 minus e to the minus t over RC, that growth function always looks like that. That's just useful for you to know in general. What is the current in the resistor after t equals 6 seconds? All right, well, I is equal to I naught e to the minus t over RC. That is, by the way, a decay function. So the current starts out big and it gets smaller. The initial current, I, is V naught over R. That's 16 over 4. Actually, it's 4 mega ohms, so that's going to be 4 microamps. So I have 4 microamps e to the minus 6 over 8. 8 is 2 times 4, RC 8. So we get 1.89 or 1.9 microamps. RC circuit requires 30 seconds to fully charge. That's going to be 10 times its time constant. So 10 tau is equal to 30. So tau is equal to 3 seconds. What is the capacitance? Well, this is equal to R times C. 3 is equal to 3 mega ohms times the capacitance. So the capacitance is 1 microfarad. Which of these statements is true? The solar wind protects the Earth from high energy particles. No, that would be the magnetosphere of the Earth. The solar wind actually are the high energy particles. The North Pole is also the northern magnetic pole. That's not true. It's actually the southern magnetic pole. Moving charges generate magnetic fields. Yeah, that's correct. So D is the right answer. Magnetic North Pole of the Earth, nearest the geographic North Pole corresponds to which of the following? All right, so remember the Earth, if this is the north, this is the south, if I imagine that there is a bar magnet in the Earth, that bar magnet is actually opposite the geographic pole. So the geographic North Pole is the magnetic South Pole, so 12 is B. You have 4 wires, and I want to know the magnetic force that is exerted on wire A. So each of these 3 wires is going to is going to create a magnetic field at this point. This wire, excuse me, will create a magnetic field that is in this direction. This wire will create a magnetic field that is in that direction, and this wire creates a magnetic field in that direction. So you have these 3 magnetic field vectors. Those 3 combined are going to generate a magnetic field in this direction. So I have a current that's out of the page and a magnetic field that is down. Current magnetic field is down. That's going to give me a force to the right. So C is the right answer there. Electron travels in the negative x. First, electron travels in the negative x direction in a region of magnetic field that is directed in the negative z direction. The electron will experience a force that, if I do my right-hand rule, I get down, but it's an electron, so I take upwards. And I was nice, I didn't give you down as an option, so you should have noticed that was a problem. What is the initial direction of this positively charged particle? All right, well, index finger, magnetic field down, that's going to be into the page for number 15. 2 kilocoulomb charge moves up with a speed of 4 meters per second. Magnetic field. Oh, and then I have an electric field I turn on. All right, so there are a couple of things that are going on here. I first need to figure out what is the magnetic force. So there's a magnetic force acting on this particle that if I'm doing my right-hand rule, I see that it is to the right. So FB is in this direction and is equal to QVB. I can calculate that magnetic force as 2 times 4 times 3. That's 2 coulombs times 4 meters per second times 3 Tesla. That's 24 newtons. But then there's another force that's acting on this. I have an electric field that is in this direction. You know, it's common to pair up magnetic and electric fields so that you have two forces, and you can manipulate those forces to move this particle in various places that you want to move it to. Anyway, it's a positive charge, so a positive charge is going to feel a force in the same direction as that electric force, and that electric force is equal to Q times E, which is 2 coulombs, times the electric field, which is 4 volts per meter, or 4 newtons per coulomb if you prefer, and so that's 8 newtons. Because these are in the same direction, I'm going to add them up. If they were in opposite directions, I would subtract them, and so C is the right answer. Okay, so this one's just calculating the force. So I have 2 microcoulombs times V, which is 4 Tesla, times B, excuse me, I got that mixed up. That's B, and then V is 5 times 10 to the 6 meters per second, times the sine of the angle. That's 8 times 40. We get 35 newtons. D. Positive particle moves in magnetic field or mass spectrometer. There's the various things about it. What is the particle? So I know that QVB is equal to mv squared over r. My v's cancel there, and I can solve this for the mass to charge ratio. M over Q is equal to BR over V. I think that's right. Yeah, M over BR over V, yeah. So that mass to charge ratio is the magnetic field, which is 6, times the radius, which is 0.5, divided by the speed, which is 18. So that's 3 over 18, or 1 over 6. So I'm looking for something with a 1 to 6 mass to charge ratio. That's a 1 to 3, that's a 3 to 1, that's a 9 to 1. Oh, here we go. So eta is this unknown particle. What is the sign of this charge? Let's just imagine this part. So I have a velocity in that direction, a magnetic field in that direction. So the force acting on that particle would pull up right here. And here it would go like that. And that's how the particle is moving. So that is a positive particle. And then which of these statements is true? This is not true. I can only determine the mass charge ratio. This is not true either. It's a centripetal force, so it only changes the direction. And so this is the correct answer. So number 20 is D. All right.